our session chair for the parallel session 4, Dr. Joseph Silikwin from the Penn State University, USA. Sir, can we start the session now?
Yes, ma'am. I'm here and present.
Okay. So we can start the session from the first paper, that is a deep learning approach of automatic scope angle identification.
Thank you, ma'am. Can I start now, ma'am?
Yes, I guess, sir, uh, can he start his presentation?
Yes, you can start. Thank you.
Thank you very much, Dr. Squiles. Good morning here now in the Philippines. So yeah, I'm here to present a deep learning approach for automatic scoliosis cab angle identification. In behalf of my co-authors, I'm Renato R. Maaluy III of the College of Engineering from Southern Luzon State University from the Philippines. So the spine is really a critical part of the body. It provides structural support and performs numerous essential roles. So scoliosis is a malformation of the spine characterized by lateral curvature as can be seen on the figure. So based on statistics, approximately 470 to 5,200 individuals worldwide per 100,000 are affected by these abnormalities. So to measure the severity of scoliosis, so two tangent lines are being measured from the most tilted upper and lower vertebrae end plates, or the cab angle measurements. So based on the conventional approach, traditional image analysis based from X-ray using mechanical devices is really time consuming, and because of the different feature extraction. So as you can see, most physicians perform manual measurement. They use protractors and rulers for the assessment and identification of scoliosis, which presents several challenges. So several challenges because of X-rays have anatomical variance. So it makes difficult to dependably quantify the extent of the abnormalities. So moreover, instrumentation and vertebral movements, patient's posture, and positioning accounts to measurement errors. So according to literature, there's an 8-degree variation in manual of measurement of cab angle by experts. So AI has the potential that can benefit medical diagnosis. So it can pave the way for improve healthcare opportunities. So as part of the Industry 4.0, so it can assist with early, fast, efficient diagnosis of X-ray, magnetic resonance imaging, and other related scans. So majority of existing solution for scoliosis measurements are mechanical. They have constrained parameters. Based on literature, also patch-based approaches, they lose contextual information on the process. So furthermore, existing methods are less effective for medical applications due to their poor accuracy and loss of detailed information again during the process. So we propose, or our research differs from previous studies by minimizing the physical intervention by developing an accurate end-to-end approach for scoliosis severity detection using machine learning for rapid and reliable medical diagnosis. So how do we arrive with this research? How do we do this? So we acquired 210 grayscale 2D spinal images exhibiting scoliosis in the AP view, 1920 by 1080 pixels. So each samples include a complete picture of thoracic and lumbar vertebrae, where most scoliosis cases occurs. So we have 180 training sets, 20 test sets, and 10 validation sets. So the data we acquired are already annotated with the experts cab angle measurement. So we will compare the experts measurement versus our machine learning approach. So the first step is to isolate the spinal region. So we reduce the size of the X-ray approximately 27.75%, because we only need the spinal portion, not the whole X-ray. So we done that using aggregated channel feature ACF, as you can see in the figure, using LUB. So we extracted the attribute vector, then use an ADABUS classifier to identify the region of interest for cropping. As you can see, the crop region, only the spinal scans remain instead of the lungs and other parts, so that we can reduce the noise because we are only interested in the spine for the cab angle measurement. So for the spine boundary identification, so we locate a vertebral segment to form a center line. As you can see in figure A, we superimpose a series of rectangle windows in order to trace a center line from upper to lower spine. Then a search is launched for the next active points between the identified pixels. So we use a 10 by 4 pixel window section, and we also use a polynomial pitting to detect the edges of the spine. So the process is repeated until all possible touch points on the center segment line is examined. So a reconstruction of the current matching window is performed until all spine limits are identified, as can be shown again in figure D. So for the vertebrae segmentation, so once we have the spine edges, so next we define a midpoint line to isolate the spine's foreground region. So we remove the ribs. So we done this by equally subspacing lines to produce three separate subsections, as you can see in figure C. Then we detect the edges of the vertebrae in order to identify the initial vertebrae detection, as you can see in figure E. These are only initial boundaries, not yet the proper segmentation process. So we altered a standard unit for segmentation purposes. So the difference of our approach is that we have the encoder, we downsample using convolution, and a decoder at the right side of upsampling. I really want to discuss this, but because of limited time, you can see we can see the details of this in the proceedings. So again, we use tenfold cross-validation to assess the segmentation performance. So if you want to perform this one, so we already defined the hyperparameters based on our data sets. So learning rate, 100 epochs, 10 batch size, 0.25 dropout rate, and also L2 norm loss function. So we benchmark three convolutional network, the standard unit, and also our proposed modified residual unit and the dense unit. So for the cab angle calculation, so we identified the MBB, or the minimum border bounding box, for the upper and lower vertebrae border. So when specific borders are defined, so we identify the most tilted vertebrae, the upper and the lower most tilted vertebrae, based on the equation number 3, where x is the slope of the upper vertebrae's upper border, and the xj is the slope of the lower vertebrae's lower edge. So for the segmentation performance, we use standard metrics for image processing. So dye similarity, Jacquard similarity, and mean squared error. So for the spine curvature evaluation, or the cab angle, so we compare the precision measurements against the machine learning measurement. So also for t-test and mean absolute percentage error for 10 validation set. So for the result, so based from the result, our residual unit perform based on DSC and JS similarity index. So the higher the value of this evaluation result, the better. Then the lower the value for the mean squared error, which is the better. So unanimously, it was the residual unit. So in terms of training time, so 25 minutes for unit, residual 30 minutes for the dense
Excuse me,
unit.
sir.
Yeah.
Excuse me, I'm sorry. We need to try to pick up the pace a little bit here.
Okay, sir. So for
Okay, thanks.
for the testing time, 0.02. So for the top bottom vertebrae reference evaluation, so the machine learning methods only deviates 0.6 in terms of error in the top vertebrae identification, and 0.5 lower vertebrae, which is very small. So t-test value, means comparing the group of medical expert and the deep learning measurement. So no significant difference at 0.09 at 0.05 levels. So mean absolute difference of only for the 10 validation set of 1.57 degrees, lower than the literature variation of 8 degrees. So here are the sample measurements. So we use the Turtle Graphics network of Python and an algorithm for angle measurement for the detection of the lines. So this research established that our approach could automatically measure cab angle using intuitive procedures. So empirical results that the residual unit, the modified, is able to recognize the internal and vertebral structure with 92.95% accuracy. So our test demonstrated that the comprehensive and optimized procedure, so we have spinal isolation, spine boundary with different methodologies, produces accurate cab angle measurement with 91.81% by mean absolute. So our pipeline validation was confirmed also with t-test with a lower value of 0.028. So no significant difference between manual and our deep learning approach. So we also discovered that although dense unit is very complex, it did not necessarily lead to accurate segmentation because each CNN has a specific strength and weaknesses. So like any research, we encountered the challenges of noisy X-ray scan. So due to insufficient image quality and patient's unbalanced posture contributing to forecast deviation. So we did not explore the issues of image reconstruction, enhancement, and reorientation correction. So for the conclusion, so an accurate prognosis of scoliosis severity is crucial for medical practitioners' treatment and planning of scoliosis. So traditional cab angle measurement is very time-consuming and manual. And we have some discrepancies because of physician subjective experience and perception. So we develop automatic pipeline for accurate cab angle measurement based on residual unit architecture. So we produce a dependable and simplified scoliosis severity identification without physical intervention. So it can assist doctors and clinical practitioners to better understand scoliosis and its treatment. So for future work, we plan to improve the model's accuracy by increasing the number of training sets and better segmentation and CNN's performance. So thank you very much for listening.
Thank you very much. I appreciate it. A little bit long, but very good points. And I'm interested to see you continue this. Looks like very promising in the medical field.
Thank you, sir.
Thank you.